Hi, everyone. I'd like to welcome Professor Yu Cui from Stanford to give us a talk today. Professor Cui is one of the most famous young scientists working on nanotechnology area. He got his bachelor's degree from University of Science and Technology of China and got his PhD degree in chemistry from Harvard University. Professor Yu Cui is right now an assistant professor at Stanford University. Let's welcome Professor Yu Cui.
First of all, let me thank Chuck for his invitation. It's a pleasure to be here. The first impression I have after I got here is Google is a really dynamic place. That's probably the most impressive point I have seen after I visited so many companies. It's also great to see several alumni from University of Science and Technology of China sitting in the front. That's a big plus for me. So in return, I'd like to tell you what I'm doing in the last several years also using nanowires and nanocrystals for nanotechnology. This is the title. But I do recognize this is a talk it's like general public talk. It will be a good idea to give you some introduction about the history of nanotechnology. First of all, what's nanotechnology? At the most general level, the nanoscience and technology, it's defined by the size scale. It's defined by this nanometer unit. Usually, it's defined as a science engineering on the 100 nanometer scale or below. So it's the size regime between the atomic level and the bulk level you have seen. So 1 nanometer is around 1 out of 10 to the 9 billion meters also. So to give you an idea how small it is, if you like soccer, you probably are very familiar with this picture. So if Zidane still have some hairs, so the size of the hair is around 50,000 nanometer also. That gives you an idea. Nanometer unit is really, really small. And how small it is. Now let me give you some example to let you build up the intuition how small nanometer is. You probably all learn about atoms. Atom has the size around 0.1 nanometer also. So going up, you start to see nanometer regime. The size of the nanometer regime includes typically molecules, DNAs, for example, proteins, and currently a really active research area carbon nanotubes, quantum dots, proteins, they're all in this nanometer regime. Going up slightly to 10 nanometer also, semiconductor nanowires and all other nanowires I'm going to talk about in just a few minutes. And viruses has the size close to 100 nanometer also. The Pentium 4 chip have the size around this 100 nanometer to a micron also. And going up, single biological cells has 10 micron also. So 1 micron equals to 1,000 nanometer. 10 micron is 10,000 nanometers. And microfluidics, lab on a chip, the size scale is in micron scale, 100 micron scale also. Human being will be all the way to this end, right-hand side. So nanometer scale is really a small size regime. But it's not the smallest size human being ever studied. Chemists and physicists used to study the size scale and the atomic size. So that's smaller than 1 nanometer. And we are also very familiar with the size regime, very, very big size regime. So nanometer regime is really between the atomic size and the bulk size. That's something you expect new properties happen. You can take advantage of these new properties to come up with new applications. So look back the history of nanotechnology. People working in this field always used Feynman's encouraging speech as the starting of the nanotechnology. So in 1959, Richard Feynman, a physicist in Caltech, gave this famous speech. He described the importance when you decrease the size of material, size of the objects to really, really small. You can do something new, you can do something important. So I highlight this sentence right here. You can decrease the size of things in a practical way. I now want to show that there is plenty of room. What he means plenty of room is there's plenty of things you can do in this size scale. So after he gave that speech, Feynman used his own money to set up a Feynman Prize, two Feynman Prizes. So anyone who can do one of these two things will win this prize. So the first one that was in 1959. Anyone who can build a motor that will fit into the size of 1/64 inch by 164 box. And the second one is anyone who can write a page of text with letters that are small enough for the Encyclopedia Britannica to be printed on a pinhead size. As soon as Feynman announced these two prizes, and the first one got claimed right away. Bill Macmillan did a really good job just by using hands to make a small motor, which is small enough to fit into the size, to win the Feynman Prize right away. But the second Feynman Prize didn't get claimed until very late, until 1985. So that's some 20, 30 years later. Tom Newman and Fabian Pease, fortunately, Fabian Pease is a professor at Stanford. I got to meet him a couple times a month. So use EB lithography to write a part of A Tale of Two Cities in the length scale required by Feynman. So they claimed the second Feynman Prize after a couple of decades. So what's the big deal about decreasing the size of objects? So what's the big deal of this nanometer scale size? Let me use one most important example to illustrate the importance of decreasing the size of the object. You all know about the first transistor. The transistor was invented in Bell Lab on the Christmas Eve of 1947. So the inventors won the Nobel Physics Prize in 1956. The first transistor is really, really big. So you can just use your hands to catch it. So over so many decades, people keep pushing down the size of transistors. Nowadays, state-of-the-art transistor fabricated by Intel has the gate length around the 30 nanometer or below. And so all the important length scale right here, like the gate dielectric thickness, a couple nanometer, and the source and drain contact all gets very, very small. So it's due to this development, due to the decreasing of the size, you can make more and more powerful transistors, more and more powerful computer chips. And decreasing the size allows you to pack a lot of things within a tiny areas. So along this line, along the line of electronics, integrated circuits is the most famous example. What important things you can do when the size gets small. So you can integrate things together into tiny areas. Jack Kirby won the Nobel Physics Prize in 2000 for the invention of integrated circuit. So it's the size decrease which drive the transistor smaller and smaller, and the transistors, the computer chips become powerful and powerful. This comes to the most famous Moore's law. It describes about every 2 years or so you can double the number of transistors within the same chip. So giving this example, now what does nanotechnology do? So people have developed the transistors get down to about 30 nanometer size scale also. So what nanotechnology do is it would like to develop the new tools to study, to see the size and the deep nanometer scale, even atomic scale. And also, the second area is to produce the structure in a nanometer scale size. You can use photolithography to pattern computer chip down to 30 nanometer scale also, but that is not enough for nanotechnology. So what are the new applications? Given you can produce these nanostructures, you have the tool to see the nanostructures. Now let me give you some of the research people have been doing in these three areas. Some of the examples just come from my own research. The first area is tools for studying in nanometer scale. The most important tools one of the most important tools is scanning tunneling microscopy. So this technique is like this. If you want to look at a sample, a substrate, you can take a really, really sharp metallic tip, scan over this sample. So the tip is sharp enough, only a single atom terminates at the tip. So you apply a voltage between the tip and the substrate, you will have current flowing through between the tip and the substrate. And by moving the tip, scanning the tip, since you have atomic size, a single atom at the tip, so you have the resolution to look at the substrate down to atomic scale. So people use this technology to look at the, for example, this is a solid state substrate. You can clearly resolve single atoms. And you can even use this tip to do something like medical operation. So you can apply a voltage to pick up an atom from the substrate and then move it, transport this atom to a new place and deposit it into a new place. By doing this, you can use atom to manipulate to form the special pattern you would like to study what happened in the nanometer scale. The inventors of STM won the Nobel Physics Prize in 1986. In the same family of scanning probe, there's another technique that is atomic force microscopy. This also takes advantage of a very sharp tip. So you use the laser to monitor the cantilever position. So during scanning the tip, you can maintain the force interaction between the tip and the substrate as constant while you are scanning your tip. If you have surface topology change, it's going to change the force. So you have a feedback loop to pull your tip up and down to monitor the surface topology. By doing this way and having a really sharp tip, you can look at the structures, for example, like proteins, like DNAs. The difference between atomic force microscopy and scanning tunneling microscopy is scanning tunneling microscopy uses the current as the signal. And atomic force microscopy is the force interaction between the tip and the substrate. So they have different usage in different areas. The inventor of atomic force microscopy is Binning, Quaid, and Gerber. Among all these inventors, Quaid is a professor at Stanford. Another technique to look at the size scale and the nanometer is the transmission and scanning electron microscopy. So you have an electron gun shooting electron out, passing a lot of electromagnetic lengths and focus down to your samples. Since the wavelength of the electrons is very small, the imaging resolution is limited by the wavelength of either light of the electron waves. So using a short wavelength of the electron beam, you can look at the structure. For example, you have a quantum dot right here down to the atomic size resolution. So this technique are really important for the development of nanotechnology. Now let's come to The second area is how do you produce the structures in nanometer scale? There are two philosophies in making things smaller. One philosophy is you can take a piece of big object and then cut it down into a small piece. This is so-called top-down approach. So going from big size to small size. Second approach is so-called bottom-up approach. You use molecular precursors, starting from molecules, and then you do chemical synthesis. These precursors start to nucleate and grow into the nanometer scale size object. This philosophy, these two philosophies represent different ways and doing almost the same thing. The industry has been motivated by the top-down approach. The whole transistors development is really relying on the top-down approach. It's the bottom-up approach, and the last 10 years also really make the nanotechnology really, really exciting. You can do something new using this bottom-up approach. So I'm going to skip how people do the top-down approach. You're probably all familiar with photolithography idea. Now let me come to the bottom-up approach, how people produce nanoscale structures, nanoscale materials using bottom-up approach. One example is the carbon-60. Carbon-60 was discovered by these three people. They are the winner of a Nobel Chemistry Prize in 1996. So taking a graphite structures, graphite has a layer-by-layer crystal structure. If you use laser to evaporize graphite, you have certain catalysts around. You can produce this beautiful, about 1 nanometer size also, a ball of, people call it a Bucky ball. So it has 12 pentagons and 20 hexagons. It is exactly like a soccer ball. This structure, this Bucky ball has a beautiful structure which is beautiful enough to get awarded a Nobel Prize to these people. And second important nanomaterials is carbon nanotubes. Carbon nanotubes is a structure also based on the graphite. If you take a piece of graphite sheet and then roll it up, it will become a nanotube. Depends on how you roll it up. You can get different chirality of tubes, and you can have semiconductor behavior, you can have metallic behavior. So carbon nanotubes becomes a very active research area about 10-15 years ago also. So another type of nanomaterials I have been working on in the last 3 years also while I was still a postdoc at Berkeley is semiconductor nanocrystals. So this tiny crystal has the size between about 1 to 10 nanometer also. It's based on purely chemical synthesis and a very hot organic surfactant. You can inject molecular precursor into this flask. And these precursors decompose to nucleate and grow into these so-called zero-dimensional nanostructures. And depending on what kind of molecules and surfactant you have in a solution, you can produce spherical shape quantum dots, nanorods, one-dimensional structure, or even branch structure. We call it, in this case, it has 4 arms as a tetrapod. Now, one more type of nanostructures produced by chemical synthesis, produced by a bottom-up approach, is semiconductor nanowires. There's many ways to make one-dimensional nanowires. One particular powerful way I have been working on is the so-called vapor liquid solid growth of nanowires. It comes from the ideas. You can take a tiny, tiny seed particles, nanoscale particles, function as a catalyst. For example, if you want to grow silicon nanowires, you can take a gold nanoparticles and heat it up above, say, 400 degrees C also, and pass silicon precursors. It could be silane. And these precursors decompose and deposit into gold nanoparticles. If you look at the phase diagram, when you mix gold and silicon together, they melt at really, really low temperature. Gold alone, the melting point is about 1,000 degrees C. And silicon alone, the melting point is about 1,400 degrees C. But when you melt these two things, you mix these two things together, the melting point is 360 degrees C. It's really, really low. So using these properties, at about 400 degrees C also, you can add silicon into gold and then make a liquid droplet. So if you keep adding silicon into this droplet, then silicon supersaturate, it's going to nucleate and grow into one-dimensional nanowire structures. It's due to this tiny size which defines the nanowire structure. Here is the transmission electron microscopy image showing you a gold particle at the end of silicon nanowires. And you can produce beautiful single crystal nanowires. So there are other nanoscale structures made by nature in addition to this artificial nanostructure made by human being. The DNA is one type of powerful nanostructure, proteins and viruses and organic molecules. So given all these structures, what kind of things you can do? What useful things you can do to the human being? So you have carbon nanotubes, semiconductor nanowires, semiconductor quantum dots, DNAs, proteins. You have carbon-60s. So over the last 15 years, people have been really creative in using these materials for different type of application. Now let me give you several examples. So I give you a list right here. The top two, cosmetics and catalysis. It's not something new. It happened for really a long time. It's there. And the new things is in the area of nanoscale electronics, molecular electronics, biosensors for healthcare and biowarfare detection, and renewable energy and battery technology, for example. So I don't need to say too much about cosmetics, just by pointing out, the sunscreen you use has nanoparticles in it. So nanoparticles, which has the semiconductor nanoparticles, has the semiconductor band gap large enough, which can absorb UV light, can be good materials as sunscreen. So remove the UV light and protect your skin. And for catalysis, the whole oil industry relies on this technology. They use metallic particles function as catalysts for cranking up the oil and decompose them into different components. So it's a big industry already. Now for better and faster transistors, people have been demonstrating using carbon nanotube. One of my colleagues at Stanford University, Hongjae Dai, and Stanford Chemistry, have shown using carbon nanotubes, you can produce the transistors, which is way more better than the transistors Intel can make. Since carbon nanotube has these graphite structures, it rolls up as a tube structure. There's no surface dangling bond on the surface. So that means when electron is moving along the nanotubes, they won't get trapped. That also means electron can move very, very fast in nanotubes. So using nanotubes, contact by two electrodes, one is drain, the other is source, and you can have a gate electrode, whether it's using substrate as a gate or you can fabricate so-called top gate. People make really high quality of transistors and demonstrate the mobility is like infinitely high because the transport of electron doesn't get scattered along the nanotube. It's like ballistic transport. And many companies are pushing very hard, especially IBM, try to use nanotubes for the next generation of transistors. And another example coming out of my own research work is to use semiconductor nanowires for making better transistors. Carbon nanotubes are nice. Their performance are very well. But carbon is a new material for the whole silicon industry. So why don't we just use silicon nanowires? Because anything related to silicon has been developed. All the etching process, all the chemistry, all the fabrication. So during my work in PhD, I actually demonstrate using a silicon nanowire contacted by 2 electrodes. You can fabricate a transistor which is also better than the current N-tail transistor. So the mobility of the charge carriers becomes higher. That also suggests you can have faster transistors. The reason for that is it's based on the same material, it's silicon nanowire. The reason it can be better is really due to when the size of this nanowire gets smaller along the cross-section. So the quantum confinement changed the electronic structure of silicon. So it makes the continuous energy band become a discrete energy band. This decreases the probability of electrons got scattered when they are transported along these nanowires. We are still developing this in this area, try to make better transistors for the next generation of a computer chip. So I mentioned to you, for all the nanostructures, molecules is one type of nanostructure. They have size scale around a nanometer also. In the last 10 years also, several research groups, especially Jim Heath's group and Caltech, and Startup Williams group and UCLA, Williams Startups group, Stan Williams group, and HP, they're developing molecular electronics and try to use really tiny size of molecules function as a switch. And this structure, this yellow color indicates the metallic electrodes. So this indicates the molecule. So they sandwich molecules between 2 sets of electrodes. Try to apply a voltage to induce the change in the molecules. They can store information right there. They can make the switch. This also is a very active research area. So due to the work in the area of nanowires and molecules, and this work made into the cover of Science in 2001. So this is rated as the breakthrough of the years, using nanowires and molecules as transistors, as switches to make better electronics. So I would hope someday, you can really, get these transistors, make them small enough, make them powerful enough, make them reproducible enough, make them dense enough to produce better and better electronics. It should go beyond iPod Nano. So it has a nano in it, but it's not really the nano we are looking for yet. So after giving you the examples of the application in electronics, if you ask me how long would you predict, the nano can do something for the transistors, replace N-tail transistors, I will tell you I don't know. It's going to be very long. Doing electronics is probably the hardest things in nanotechnology. It's the major driving force 10 years ago. But now the driving force comes from all the directions. So electronics probably is the latest areas you can impact in nanotechnology. Other areas of technology might be possible, might be earlier than the electronics. One area is in biosensing for medical care, for human health. Now let me give you one example coming out of my own research. So we made this a one-dimensional nanowire structure, semiconductor nanowires. You all know semiconductors has field effect. So if you apply a voltage, you apply electric field close to the semiconductor, you can change the charge carrier concentration in semiconductor. You can change its conductivity. Using these ideas, if you take a nanowires contacted by 2 electrodes, and then you put certain receptors which function as a recognition reagent to recognize certain molecules you want to detect, if this molecule comes in and bind onto these receptors, if these molecules have charges, it's going to function as a gate voltage function. It will have electric field to interact with nanowires, change the calorie concentration in nanowires. By measure the conductance, you will see the conductance change. You will be able to detect the existence of these red color charged molecules. So based on these ideas, we think we can develop a new type of sensors. Since the nanowires are so small, they must be really, really sensitive to any charged molecules. So we know the proteins, DNAs, they have charges. So this is the idea for detecting something in the human body. The advantages of this technique is, since the wire is small, it's sensitive, as I mentioned. And second, this is purely based on the electrical current and conductance measurement. You don't need to label any molecules. This is really different from the existing current technology. So they need to go through extensive radioactive labeling, for example. So a nanowire sensor doesn't need to do that. And imagine if you can bring a lot of nanowires together, you can do array-based of sensing. If you have 1,000 of this nanowire, each one has different receptors, you can detect different molecules at the same time. Here's one example. We were doing the cancer marker detection. So for many types of cancers, before the cancer really developed to the late stage, the human body already has some change in the blood. For example, for prostate cancer is a killer, and it's a killer in US for the man. It has a specific cancer markers. It's called prostate. It's called PSA, prostate specific antigen. It's a protein. If a man gets a prostate cancer in the early stage, this protein concentration will go up. So if we can find the antibody, we label the nanowire with the antibody of these cancer markers, then you can detect it in a really early stage. So here I show you one example. Having 3 nanowires, each nanowire modified by different antibody, they can detect different cancer marker antigen. They are all proteins. Indeed, you can do that quite successfully. Here you can just simply measure the current, or say conductance, versus time, and different time, and you flow in the different cancer markers onto the nanowires. For this nanowire number 1, it has a PSA antibody. So when PSA goes in, you see the conductance goes up. But the other 2 nanowire doesn't have response right here. And you can do the same thing for the other 2 nanowire, have different cancer markers, like CEA comes in and MUC comes in. It corresponds to different type of cancer. So you can detect them really well. Indeed, we can go down to the concentration, about picogram per mil, and even close to femtogram per mil. It's like 100 times more sensitive than the current technology. So using this nanowire sensor detection scheme, it's possible to discover cancer in really early stage. So biosensor is a big area. Another big area just coming up, become hotter and hotter, is the energy-related areas. As the gasoline price goes up, you all understand why this area is important. The key things for making solar cells, collect sunlight energy and make it into electricity, is to come up a way you can collect the sunlight and convert it into electricity and really high efficiency with very, very low cost. That's something nano can do. So we made these nanowires, we made these nanocrystals, especially nanocrystals that dissolve in organic solvent. They can be processed as chemicals. If you want to make a solar cell, what you do is you take a substrate, a glass, and then you just spin coat these nanocrystals, or just simply by printing. Spin coat and printing is very, very cheap technology. So you can cover really large areas. And for example, making solar cells for all this window converted into solar cells. And that's what nano can do. In this example, you mix nanoparticles, nanocrystal together with organic polymer. So organic polymer and nanocrystal will form a junction. And this junction, if you look at its electronic structures, this junction can separate electrons and holes to create electricity. Electrons and holes are created by sunlight. When sunlight comes in, the photon energy create electron and hole pairs, excite them. And then you separate them, you can collect as electricity. So my postdoc advisor, Paul Vasatos, was working really hard at Berkeley in these areas. And my research group, I also have a program and doing that too, but with different ideas from Paul. And my colleague, Mike McGee at Stanford Materials Science, is an expert in using an organic nanostructure blend together with polymer to make better solar cells. So what about for battery? You're all familiar with a lithium-ion battery now. You know, the laptop you have is powered by lithium-ion battery. So all your cell phones are powered by lithium-ion battery. Lithium-ion battery really dominate the portable electronics. Now we are thinking very hard, can we use lithium-ion battery for doing something even bigger? One area is electrical vehicles. Can you use battery to power vehicles as the sole power source instead of using gasoline? Gasoline is really polluting the whole world. About a quarter of greenhouse gas comes from the transportation consumption and gasoline. So it would be nice if you can use battery to power the electrical vehicles. But what's the critical problems in batteries? One critical problem is you need higher energy and power density. Higher energy density means you want to have a battery in your car, and then you can drive for 300 miles without charging it. You don't want your car to be charged like every 50 miles. That won't be good. And higher power density means if you want your car to accelerate to a certain speed, you really need to crank up the power a lot. The current battery technology is not good enough for doing that yet. Of course, you want it to be cheap. And the current technology, battery technology, is not cheap. Current lithium-ion battery technology is using lithium cobalt oxide. Cobalt is very expensive. It's toxic. And also, there's not enough cobalt in the world to supply to go into electrical vehicles. So we are coming from the nanotechnology standpoint. We want to impact these areas a lot, especially to improve the higher energy density and power density. When you look at the problems in lithium-ion batteries, how can you increase the power, for example? So power is like if you have higher current, you get higher power. That also means if you can get lithium very fast into the electrode and out of electrodes, the battery electrodes, then your power gets higher. So the key thing is you want to maximize the surface contact areas between the battery electrodes and the electrolyte. So that's what nano can do. Nanomaterials has really high surface to volume ratio. So surface area is high. So it can have high interfacial area with electrolytes. So in my group, we are using nanowires and contact by this red color electrolyte. So you can see the surface area get increased by a lot compared to the current lithium-ion battery technology. By doing that, we hope the power density can go higher. We also have the reason why the energy density can go higher. I probably just don't have time to mention that to you. So we are also looking in the areas trying to make a better non-volatile memory. And I'm going to just skip this and come to the conclusion. So I give you the examples in 3 areas of active research. Develop the tools for nanotechnology, produce nanostructure and the structures in nanometer scales. So the first two areas are pretty much more or less mature. So we know how to make nanostructures. We have really powerful tools to look at the nanostructure. What we need is, can we really impact the application with nanomaterials? That's the key thing. The public has been looking into nanotechnology for a while. They're eager to see some meaningful, some critical application coming out of the nanomaterials. So this application can range from transistors, non-volatile memory, battery technology, solar cells, and biosensors. It's hard to predict which one will stand out first, but all of them all have the potential. So thank you for your attention, and I will be happy to entertain any questions.
Any idea what the relative efficiency of nanotechnology-based solar cells are versus conventional cells that are manufactured now?
The nanotechnology-based solar cell is low at this moment. So conventional solar cell, if you look at a single crystal silicon, it go up to 18–19%. Polycrystalline silicon about, say, 12% also. And the current nanotechnology solar cell based on the organic polymer blend together with inorganic structure go up to 5%, 7%. There's still a long way to go for nanotechnology solar cells. But coming back to the history of the nanotechnology solar cell, it's not that long. It's only like 5 to 7 years or so. So it certainly still has the potential to go higher. Okay, thank you.
Thank you. Thank you.